Welcome back to the deep dive.
Great to be here.
Today we're plunging into a topic that's really fundamental to the future of AI, especially large language models, LLMs.
Absolutely critical stuff.
And as always, listeners, we'll be zeroing in on the technical details, the mechanics, the implications of the tech itself. We're going to sidestep the ethical debates and inclusivity discussions today to keep our focus sharp.
Right. Purely the how it works and why it matters technically.
Exactly. So imagine for a second you're building this incredibly powerful engine. I mean, something that can write code, generate amazing text, maybe even art, almost like a human.
Yeah, the capabilities are astounding now.
But then you hit a snag. You realize you need a really, really finely tuned steering mechanism, like a super precise navigation system to make sure this powerful engine goes exactly where you want it to. It needs to align perfectly with your intentions, your subtle preferences, maybe even things you didn't explicitly state.
That's the core challenge, isn't it? Alignment.
That's precisely the challenge we're facing with LLMs and human preferences. Getting these super capable AI systems to genuinely get and act on what we want, the subtle stuff, the complex stuff, it's not just a nice feature.
No, it's essential.
It's a massive technical hurdle if we want AI that's actually useful, predictable, reliable when you roll it out widely.
It really is a fascinating landscape. And what's become pretty clear, I think, is how reinforcement learning from human feedback, RLHF, has kind of emerged as the main way people are tackling this.
Right. RLHF is everywhere now.
It is. And you can think of it like teaching by example, but, massively scaled up. Instead of trying to write down every single rule for good behavior or crafting these complex reward functions by hand.
Which sounds impossible for language.
It pretty much is.
Yeah.
So instead, RLHF lets these models learn what we want just by watching and adapting to our choices. You give the AI a prompt, it gives maybe 2 different answers.
Or more sometimes.
Or more. Yeah. A human looks at them, says, I like this one better, and the AI learns from that simple preference signal.
So it's learning directly from judgment.
Exactly. It's a powerful, data-driven way to get beyond rigid programming and hopefully capture what humans actually value in a response.
Okay, but here's where it gets really interesting and maybe a bit concerning. What if the way we model those human preferences in the standard RLHF setup, what if that foundation is, well, a bit shaky?
Shaky how?
What if we're making a built-in assumption about how people make judgments, an assumption that just doesn't really hold up when you look at real, messy human preferences?
Okay, I see where you're going. This is a known issue.
Right. So today we're doing a deep dive into a really innovative new approach. It's called Nash Mirror Prox, or NashMP for short.
NashMP, yeah.
Yep.
It's been getting some attention.
And it tackles this foundational problem head-on. The promise is a faster, more stable, and maybe ultimately more accurate way to align LLMs because it completely rethinks how we should capture and use human preferences.
It's a significant shift in perspective, moving away from some classical assumptions.
Definitely a technical leap, and we're going to unpack exactly why it's potentially such a big deal.
Sounds good. Where should we start?
Let's start with the standard way, the conventional RLHF approach. So typically, the setup involves creating what's called an underlying reward model.
Right, the RM.
The RM's job is basically to assign a number, a scalar reward, to different outputs the LLM might generate.
Simple idea on the surface.
Yeah, it seems straightforward. If you, the human judge, prefer output A over output B, the system learns to give A a higher number, a higher reward than B.
And the difference between those numbers supposedly captures how much you prefer A.
Exactly. And a very common choice for building this reward model, something you see cited all the time, is the Bradley-Terry model, the BT model.
Ah, yes, Bradley-Terry. A classic from statistics, actually predates AI by decades.
Right, and it simplifies things nicely. It assumes the probability of preferring A over B is directly linked to the difference in their hidden reward scores.
So if response X gets a reward of 7 and Y gets 5, the BT model says X is preferred because, well, 7 minus 5 is 2. A positive difference.
Simple, quantifiable. And the goal then, using this BT model, is often to find what's called a Condorcet winner.
Right. The Condorcet winner concept comes from social choice theory. It's the option that would beat every other single option in a head-to-head matchup.
So you want the AI to ideally always produce that one best response, the one that maximizes this inferred reward, the one that wins all the pairwise comparisons based on the model.
That's the ideal picture, yes. A single, clearly best output defined by a consistent reward function. Tidy.
But It's not always that tidy, is it?
No, not at all. And this is where we hit that significant and maybe often glossed over technical limitation of using something like the Bradley-Terry model.
The core assumption.
Exactly. It fundamentally relies on an assumption called transitivity.
Okay, unpack transitivity for us.
Sure. Transitivity is pretty intuitive logic, actually. It just means if you like A better than B and you like B better than C, then logically you must like A better than C.
A leads to B leads to C, so A must beat C, like a straight line.
Precisely. AB, BC implies AC. It feels like how rational choices should work.
But the key word there is should.
Right. Because real human judgment, when you actually measure it, is often not transitive. We see these things called intransitive preferences all the time. Those neat ABC chains break down.
So the logic fails.
It's not really a logic failure in humans. It's more that our preferences are complex, multifaceted. Think about Gardner's paradox with non-transitive dice.
Oh, yeah, the rock, paper, scissors dice?
Kind of like that. You can have die A likely beating die B likely beating die C, but then, surprise, die C is likely to beat die A.
Yeah.
There's no single best die overall.
It's a cycle. A, B, C, A.
Exactly.
Yeah.
Or think about Amos Tversky's work in psychology. He showed this with choices between, say, gambles or even everyday products. Well, you might prefer a car that's slightly more fuel efficient, A, over one with a slightly nicer interior, B. Okay, AB.
Makes sense.
And you might prefer the nicer interior, B, over a slightly cheaper base model, C, BC.
Still following.
But then if I offer you the fuel-efficient one, A, versus the cheap one, C, directly, maybe the big price difference makes you choose the cheaper one, C, for overall value. So now CA.
Ah, so you get A, B, B, C, but C, A. The chain breaks.
Precisely. It happens constantly when we're balancing multiple criteria, like with LLM responses. It's more creative, more factual, more concise, better tone. You can easily get into preference cycles.
And if your reward model, like Bradley-Terry, assumes transitivity,
it just can't represent these cycles correctly. It's trying to fit cyclical data onto a straight line. It fundamentally misunderstands the preference structure.
Okay, that's already a big issue with just one person's judgment. What about when you have feedback from lots of people?
Now it gets even trickier. Because even if you imagine, hypothetically, that every single human judge did have perfectly transitive preferences, which is unlikely.
Yeah, very unlikely.
When you try to aggregate or combine those preferences across the whole group, you can still end up with collective intransitivity.
So the group's preference becomes cyclical even if individuals are consistent.
Yes. This is a really famous result in social choice theory. Think of Arrow's impossibility theorem or other aggregation paradoxes. You can have everyone on a committee rank options logically, but the committee's overall choice, based on voting, might prefer A to B, B to C, and C to A.
Wow. So there's no single will of the group sometimes.
Yeah, exactly. There's no single Condorcet winner, no option the group collectively agrees beats all others.
And that sounds like a fundamental technical barrier for AI alignment. If the very goodness signal we're feeding the AI, derived from group feedback, is inherently cyclical or contradictory,
then the AI can never truly converge to what we collectively want. It might chase its tail, trying to satisfy impossible conditions, or it might settle on something mediocre that doesn't actually reflect the nuanced preferences.
It's optimizing based on a flawed map.
That's a great analogy. If the underlying model of what's good, especially BT, is oversimplifying or just plain wrong about the structure of preferences,
Especially these intransitivities and aggregation issues.
then the AI systems we train with it might end up misaligned. They could optimize for a sort of caricature of human preference, missing the crucial subtleties.
It might hit the target defined by the flawed model, but miss the actual bullseye of what humans find genuinely helpful or appropriate.
Precisely. It could converge to an output that, in a head-to-head comparison, people might actually dislike compared to another option the model discarded because the reward model couldn't see the cycle.
Like getting stuck navigating that forest with only straight lines on the map. You'll definitely get lost.
Okay, so to get around these really restrictive assumptions of the traditional reward models, the need for a consistent scalar reward, the existence of Condorcet winner researchers started thinking differently.
Moving beyond reward models.
Exactly. They pivoted to a framework called Nash Learning from Human Feedback, or NLHF.
Nash, like John Nash. Game theory.
Precisely. It's a fascinating shift. Instead of trying to guess this single reward number for every action, NLHF reframes the whole alignment problem as a symmetric two-player game.
A game? How does that work?
Think of each player in this game as representing a policy, a strategy the LLM uses to generate responses. these two identical policies kind of compete against each other.
Compete how?
They propose actions or responses, and the outcome of this game is decided based on those pairwise preferences we get from humans. Is response A better than response B?
Ah, so it uses the preference data directly without trying to force it into a reward score first.
That's the key insight. This game-theoretic view is naturally much more robust to intransitivity. It doesn't need to assume a simple linear preference order. It's designed to find stability, even when those preference cycles exist.
Okay, that's a clever reframing. Moving from a static reward score to a dynamic game.
It is, and what's really intriguing is how NLHF changes the goal.
Right, you said it's not looking for the Condorcet winner anymore.
Correct. The objective in NLHF is to find something called a symmetric Nash equilibrium, or NE.
A Nash equilibrium, the point where neither player can improve by changing strategy alone.
Exactly that. And in this specific context, drawing from work on dueling bandits, the symmetric NE is also known as a von Neumann winner, or VNW.
A von Neumann winner. Okay, what is that, practically speaking? Is it still a single best response?
Usually no. And that's the crucial difference. A VNW typically isn't one specific action or LLM response. It's generally a distribution over actions, a mixed policy.
A distribution, like sometimes say A, sometimes say B.
Kind of. Think of it less like finding the single best dish on a menu, and more like figuring out a balanced diet. No single food is best every single time, but a good mix is stable and healthy.
So the optimal outcome isn't always picking one winner, but maybe having a strategy that involves a stable mix of different kinds of responses.
That's the idea. This distribution represents a stable outcome even when preferences are intransitive. Why? Because from that mixed strategy, no single policy can improve its expected win rate against itself by unilaterally switching to a different strategy.
It's stable against itself because of the game setup.
Yes, it's a fundamental shift. We're not looking for the universally best action, but a stable distribution or strategy that can handle the ambiguity and cycles in human preferences.
That makes a lot of sense for dealing with messy real-world feedback.
It does. But then if we connect this back to actually fine-tuning these huge LLMs, there's a big practical point.
Which is?
You definitely don't want the LLM to just forget everything it learned during pre-training.
Yeah.
I mean, these models know so much about language in the world.
Right, you don't want to throw the baby out with the bathwater while aligning it.
Exactly. And that's where regularized NLHF comes into play. It's a modification with really critical technical implications.
Regularization usually means keeping things simple or preventing overfitting, right?
Sort of. Here, the main goal of regularization is to learn a policy that aligns with the human preferences from the game, but stays close to the original reference policy.
The reference policy being the base pre-trained LLM.
Typically, yes. The model before you started the preference tuning.
Okay, how do you enforce that closeness?
You add a penalty term to the objective function you're optimizing. This penalty is proportional to the Kullback-Leibler divergence, the KL divergence between the policy you're currently learning and that fixed reference policy.
KL divergence.
Yeah.
That's a way to measure how different two probability distributions are.
Exactly. It measures the information loss when you approximate one distribution with another. So adding a KL penalty acts like a kind of tether. It pulls the learned policy back towards the original model.
Keeping it from straying too far.
Right. It helps prevent what we call catastrophic forgetting, where the model might get really good at the specific preference task, but lose its general knowledge or fluency.
So you could end up with an AI that gives perfect answers to one type of prompt, but sounds like nonsense otherwise if you don't regularize.
That's the risk.
Yeah.
But beyond just preventing forgetting, this KL regularization actually gives you some nice theoretical properties for the optimization itself.
No. Like what?
Most importantly, under certain conditions, it guarantees that the Nash equilibrium is unique.
Ah, so there's only one stable point to aim for.
Yes. And having unique NE makes the optimization problem much cleaner, much more stable. You're not potentially jumping between multiple different good solutions. The learning process has a single, well-defined target.
So regularization gives you stability, prevents forgetting, and makes the math work out better. Seems essential.
It's pretty much standard practice now for robust alignment.
Yeah.
It ensures the model adapts to preferences in a controlled way.
Okay, so we have regularized NLHF, aiming for this unique, stable von Neumann winner distribution, which respects preferences, even if they're cyclic, and keeps the model grounded. But finding that NE is still hard, right? Especially with giant models.
Oh, absolutely. It's a complex optimization problem. Some of the foundational work, like from Munoz and others, introduced an algorithm called NashMD.
Nash Mirror Descent.
Yeah, based on mirror descent. It was the big step. It gave us a way to approximate the VNW and prove something called last iterate convergence.
Meaning the policy at the very end of training is good? You don't need to average past policies?
Correct, which is nice for deep learning. But its convergence rate was O. N is the number of preference queries, is that regularization strength.
How fast is that?
It's polynomial. Think of it like this. To cut your error in half, you might need, say, 4 times the data or iterations. To cut it by a factor of 10, maybe 100 times, it gets slow.
Okay, not ideal for massive models needing tons of iterations.
Right. So this naturally led researchers to ask the classic ML question. Can we do better? Can we get faster convergence? Maybe even linear convergence.
Linear convergence, that's the dream, right? Error drops exponentially fast.
That's the gold standard. It means the error shrinks by a constant factor with each iteration or each batch of data. It's like going from a slow uphill climb to a rocket launch, comparatively. Huge difference in training time.
And could they do it?
Yes. And that's where Nash Mirror Prox, or NashMP, comes in. It's the affirmative answer.
Okay, NashMP delivers linear convergence. How? What's the magic?
Well, the insight comes from borrowing an idea from a different optimization scheme called Mirror Prox. Mirror Prox is known in optimization circles for being really good, really fast, at solving certain types of problems, specifically convex-concave saddle point problems.
Which is the kind of math problem these preference games turn into.
Exactly. And NashMP cleverly adapts the core idea of Mirror Prox. It uses a really smart 2-step iterative structure.
2 steps, not just 1 update per iteration.
Right. It's not just reacting to the current situation. Think of it like playing chess. You don't just look at the board now. You think, if I move here, what's my opponent's likely best response?
Okay.
So step 1 in NashMP is the extrapolation step. The algorithm kind of predicts an improved opponent policy. It does this using a mirror descent step based on its own current policy. It's like asking, what would my opponent do if they were playing optimally against my current strategy?
It anticipates the countermove.
Exactly. Then step 2 is the update step. Here, the algorithm updates its own policy. But crucially, it updates against that predicted, improved opponent policy from step 1, not just the current opponent.
Ah, so it's updating based on where it expects the opponent to be next.
Precisely. It's this forward-looking, predictive element that makes Mirror Prox and thus NashMP so effective. It avoids the oscillations you sometimes get with simpler methods and converges much, much faster towards that stable Nash equilibrium.
That 2-step predictive dance sounds really powerful, and the theoretical results bear this out.
Absolutely. The analysis is where NashMP really shines, especially for LLMs. First, as you said, last iterate linear convergence to that Bow-regularized NE.
Let's really nail this down. Compared to NashMD's polynomial O,
NashMP achieves a rate like O, 1 plus 2. Don't worry too much about the exact formula. The key is the n in the exponent. That signifies exponential decay of error linear convergence.
which means drastically faster training.
Hugely faster. We're talking potentially orders of magnitude, fewer iterations or data points needed to reach the same level of alignment accuracy.
And you mentioned last iterate again. Why is that so practical for deep learning?
It means the model you have at the very end of your training run is the one you use. You don't need complex procedures like averaging the model's parameters over the entire training history, which can be cumbersome and memory intensive. Just take the final model. Simple.
Okay, faster convergence, practical last iterate guarantee. What else?
This next one is massive for LLMs. Action space independence. The convergence rates, both the linear rate for the regularized problem and related rates for the unregularized game, do not depend on the size of the action space. Why?
And the action space for an LLM is the vocabulary. All possible next words or tokens.
Exactly. Which can be enormous. Tens of thousands, hundreds of thousands easily.
So if the algorithm slowed down as the vocabulary got bigger?
It would be a huge bottleneck. Fine-tuning models with massive vocabularies would become incredibly slow or even infeasible. NashMP avoids this completely. Its speed doesn't care how many possible words the LLM can say.
That's a really big deal for scalability. Wow.
It is. And one more point. Competitive query complexity. Even for the original unregularized preference game, NashMP matches the best-known sample complexity queries to find an accurate solution. So it's getting the best of both worlds. State-of-the-art efficiency in terms of data needed, plus that faster linear convergence for the regularized problem we actually care about for alignment.
So it's fast, practical, scales to huge vocabularies, and data efficient. Sounds like a win all around, theoretically.
Theoretically, yes. The analysis is quite compelling.
And does this theory connect smoothly to the messy reality of deep learning with neural networks and gradients?
It does. The researchers didn't just stop at the abstract algorithm. They provided a detailed analysis for practical, parameterized policies, like the neural networks used in LLMs.
How do you even do those mirror descent steps with a giant network?
You can't do them exactly, it's computationally impossible, so you approximate them. The paper shows how to do this using standard policy gradient methods, specifically softmax policy gradients.
Okay, policy gradients, that's standard RL stuff.
Right. And importantly, their analysis actually improves on some previous theoretical understanding of these methods. They managed to remove a problematic dependency on the number of actions, Y, in the analysis of softmax policy gradients for certain related problems.
Tying back to that action space independence again.
Exactly. It means even the practical approximations using policy gradients retain that crucial efficiency and don't suddenly become slow just because the LLM has a large vocabulary. The theory holds up nicely when translated to practice.
Okay, that's the powerful theory laid out. Linear convergence, action space independence, solid practical approximations. But theory is one thing. How do you actually make this beast run on a real multi-billion parameter LLM? What does the practical deep learning implementation look like?
Right, bridging theory and practice. As we touched on, the key is smart approximation, since you can't calculate those mirror descent updates exactly for a huge neural net.
You use gradients.
You use stochastic policy gradients, but the practical NashMP variant adds a couple of crucial ingredients, common in robust deep RL, to make it stable. It uses two policies, an online policy and a target policy.
Online and target. Okay, what's the difference?
The online policy is the one you're actively training, updating its parameters based on the preference feedback you're getting right now.
That's the main learner.
Right. The target policy is like a smoothed, slower-moving version of the online policy. It's not updated directly by the gradients from the current batch of data.
How does it get updated then?
Usually with an exponential moving average, or EMA. Think of it like averaging the online policy's parameters over time, but giving more weight to recent parameters. It creates a more stable, lagging version of the online policy.
Why have this separate target policy?
It's a stabilization trick. Using the smoother target policy in the loss calculation helps prevent the training from becoming unstable or oscillating wildly, especially because the opponent in the Nash game is effectively also changing as the online policy learns. It mimics the two-step structure of Mirror Prox in a practical, deep learning-friendly way.
Providing a more consistent target to optimize against.
Exactly. It's a very common technique in algorithms like deep Q networks, DQN, or DDPG for similar reasons. It just works well.
Okay, so EMA for the target policy. How is the gradient itself estimated for the online policy?
They use a reinforced style gradient estimator, which is pretty standard for policy gradients. But the way it's formulated here has this interesting contrastive nature.
Contrastive, meaning it compares things.
Yes. Think about a pair of responses, A and B, and the preference feedback. If the preference model says A and B are equally good or equally bad, this gradient estimator actually produces zero gradient. No update happens.
So no signal if there's no clear preference.
Right. But if response A is clearly preferred over B, the gradient does two things simultaneously. It increases the probability of generating A, and it actively decreases the probability of generating B.
It pushes towards the good one and away from the bad one explicitly.
Exactly. It's directly optimizing the preference comparison. And then layered on top of this contrastive loss, you also have those KL regularization terms we talked about.
Right, the penalty for straying too far from the original pre-trained model.
And also in the practical implementation, often a KL term pulling towards the target model as well, further enhancing stability.
So contrastive preference optimization plus regularization against both the base model and the stable target model. Seems like a solid recipe.
It's designed to be robust and effective for large model training.
Okay, so with this practical setup figured out, it was time for experiments. Does the theory translate? They started with synthetic tests first, right? Matrix games.
Yes, matrix games. These are useful because you can construct them to have specific properties. They set it up as a contextual dueling bandit problem.
Dueling bandits. Like two options competing based on preferences.
Right, and it's a generalization of something called a low-rank linear bandit. But the crucial design choice here was that the matrix games they used specifically did not admit a Bradley-Terry model.
So they built an environment where BT would fail.
Exactly. It directly creates the kind of intransitive preference structure that NashMP is supposed to handle better. It's a targeted test of that core capability.
Clever. And what did they find in these matrix games?
The results, shown in Figure 1 of their paper, were pretty convincing. Over longer training times, NashMP, especially a variant using an adaptive kappa, which controls regularization, consistently got lower suboptimality.
Meaning it found better solutions, closer to the true optimal strategy for the game.
Yes, it aligned better with the underlying complex preferences. And importantly, it did so with much smaller confidence intervals around its performance curve.
Smaller confidence intervals, meaning less random variation, more stable learning.
Exactly, more reliable convergence to a good solution. Meanwhile, they showed that online DPO, another popular method,
Direct preference optimization.
right, it actually diverged on this problem. Which makes sense, because DPO is fundamentally trying to fit a reward model, like BT. It's not designed for these non-transitive preference games.
So the Matrix game showed NashMP was stable and effective, precisely where simpler reward-based models struggled. Strong initial validation.
They're very strong. It showed the core mechanism works in a controlled setting designed to be challenging.
Okay, but the real prize is LLMs. How did NashMP fare when they moved to fine-tuning actual large language models?
Right, that's the ultimate test. They used the Gemma 2B model, a pretty capable open-source model from Google.
Gemma 2B. Okay. And the data.
They used datasets from the RLHF benchmark, which provides human preference data suitable for these kinds of alignment experiments. They used it for initial supervised fine-tuning, SFT, and then for the LLHF part with NashMP and the baselines.
And how did they judge which model was better? Human evaluators.
For the main results, they used another Gemma 2B model trained specifically as a reward preference model itself, using a robust training method. This automated judge evaluated pairs of outputs from the fine-tuned models.
Okay. An AI judge for scalability. And what were the baselines they compared
A
against?
solid list. Online DPO, online IPO, identity policy optimization, the earlier NashMD algorithm, and also regularized self-play.
Regularized self-play. How does that relate to NashMP?
Regularized self-play is actually very similar. You can think of it as NashMP, but without that ENA smooth target policy stabilization, or like NashMP with infinite smoothing. It's a very relevant baseline.
Got it. So the head-to-head results.
The results are in Table 2 of the paper, showing pairwise win rates. NashMP came out on top.
Outperforming all the baselines, including regularized self-play.
Yes. It achieved higher win rates when its outputs were compared against the outputs from all the other methods, according to that automated judge.
So the Gemma 2B model, fine-tuned with NashMP, was judged to be better, more aligned with the preferences than models tuned with DPO, IPO, NashMD, or even regularized self-play.
That's what the results indicate. And the comparison with regularized self-play is particularly insightful.
Why?
Because the main technical difference is that target model regularization, the EMA smoothing inspired by Mirror Prox. The fact that NashMP beat regularized self-play directly validates the practical benefit of that specific implementation detail.
So that two-step idea, approximated with the target network, isn't just theoretical elegance, it actually leads to better alignment performance in practice on a real LLM.
Exactly. It demonstrates superior alignment capability, validating the theory, the speed, the stability in a very practical, large-scale setting.
Okay, let's recap then. We started this dive looking at a really fundamental issue in AI alignment. How do we get these powerful LLMs to genuinely grasp and follow complex human preferences, especially when those preferences are messy, maybe even cyclical, not neatly transitive?
Right, the limitations of traditional reward models like Bradley Terry.
We saw how assuming transitivity can lead to models that don't capture the full picture, potentially leading to misaligned AI. Then we explored Nash learning from human feedback, NLHF, which reframes alignment as a game, seeking a stable Nash equilibrium or von Neumann winner, often a mixed strategy that can handle intransitivity.
Game theoretic solution.
And finally, we unpacked Nash Mirror Prox, NashMP. This algorithm brings the power of Mirror Prox optimization to NLHF.
Delivering those key benefits.
Key benefits being faster, linear convergence, that crucial independence from the massive action space size of LLMs, practical last iterate guarantees, and strong empirical results. It didn't just work in theory or on toy problems.
It demonstrated superior performance in real LLM fine-tuning experiments, outperforming strong baselines.
It really feels like a compelling technical answer, tackling a foundational problem by rethinking the assumptions and using more sophisticated optimization.
It's a very elegant piece of work, connecting theory from game theory and optimization directly to a pressing practical problem in AI.
So let's end with a thought looking forward. What are the broader implications here? If this technical approach proves robust and scalable, what does it mean?
Well, it raises a really important question, doesn't it? if we can align these incredibly powerful models with this level of precision and efficiency.
Even when faced with complex, maybe illogical-seeming human preferences.
And do it in a way that scales regardless of how many things the model could say. What does that unlock for the next generation of AI?
More capable AI.
Potentially, yes. It suggests a future where AI isn't just powerful in generating text or code, but it's also deeply attuned to the real nuances, the subtleties, the sometimes contradictory nature of human judgment.
An AI that understands us better, even our inconsistencies.
Perhaps an AI that can navigate that messy reality because its alignment process doesn't rely on brittle assumptions of perfect rationality or transitivity. This technical leap, handling complex preferences efficiently, could pave the way for AI systems that are not only more capable, but also significantly more reliable, more trustworthy, and ultimately more genuinely helpful because they understand the underlying preferences better.
Building AI that gets us, quirks and all. A fascinating prospect.
It's a crucial step towards that goal, I think, moving beyond simple reward maximization to finding stable solutions in the complex game of human values.
A really exciting development to watch. And that is a wrap on our deep dive into Nash Mirror Prox.
Thanks for the great discussion.
Listeners, if you want to stay updated on the latest AI and ML research papers, do check out our webpage. The link is right there in the bio.
Lots of cutting-edge work appearing all the time.
Absolutely. Until next time, keep exploring, keep questioning, and keep learning.